Hello, my name is Samuel Lovett, and I'd like to thank you for joining me for the presentation of my first paper, Level Plane SLAM, Out-of-Plane Motion Compensation in a Globally Stabilized Coordinate Frame for 2D SLAM. But before we begin, we need to understand what is SLAM. SLAM stands for Simultaneous Localization and Mapping. Here is an example of SLAM with a modern-day Roomba. The platform begins by making a map of its environment, and as it moves around, it localizes itself within that environment, meaning that it both knows where it is currently as well as where it has been. But SLAM isn't just for vacuums. It can be found anywhere that robots move autonomously, like similar 2D examples in factory logistics, or in 3D examples with UAVs, underwater surveying, and humanoid robotics. One of the key aspects of SLAM is scan matching. When a 2D platform like a Roomba or other autonomous vehicle perceives its environment using a LiDAR, they generate scans like the ones shown here. A scan is simply a collection of points that represent the distance from the platform to the wall, which we've represented in gray. On their own, each scan provides an incomplete view of its surroundings, but by matching them together, you can simultaneously build a better map of your surroundings, as well as determine how your robot has moved from scan to scan. And this is what that looks like. Scans are provided to the scan matcher in reference to the platform. So what I mean is that the platform is always at the origin, and the platform is always facing forward when the scan is given to the scan matcher, like you can see here. The scan matcher's job is to find the optimal 3 degrees of freedom transformation required to align the scans. By correctly aligning the scans, you're able to find the relative transformation T that represents the platform's motion between the two scans. But scan matching isn't always as easy as the animation makes it seem. In the simple 2D case, they're almost always guaranteed to have some overlap. But as scans overlap less and less, it becomes more and more challenging for scan matchers to find the correct transformation. So what if platforms are not kept level like our 2D example? Platforms like drones or wearables often experience rotational motion that cause their measurements to be out of plane of one another. How would this impact the amount of overlap seen in our scans, and therefore our scan matching performance? The answer is it would cause significant challenges to scan matching. The first challenge is that 2D LiDARs having 3D components have much less overlap between each other, meaning that it's almost impossible for our scan matcher to find the correct alignment. The second challenge is that our scans are still in 2D, even though the distance measurements making up the scans are in 3D. As this figure shows, any rotation that occurs out of plane, pitching or rolling the platform, theta or psi, causes a change in distance to our wall, d2. This distance has an x, y, and z component, but our LiDAR data only has an x and y component, meaning that the full magnitude of d2, including the z component, is reported in 2D, shown here by our black scan endpoint. We call this unaccounted for z component as out-of-plane motion. The problem with out-of-plane motion is that it quickly degrades the performance of our scan matcher. Take the black and green scans generated from our example on the right. Even if the scan matcher correctly matches these three sides, we are left with these artifacts shown here, which have a compounding effect on bad matching since the scan matcher is equally likely to match in either location. But don't just take my word for it. Here is a real-world example where you can see these artifacts at work, helping to generate a map that is completely unusable. Finally, bringing us to what you all came here for, a description of our solution, our experimental validation, and our concluding remarks. So it's clear that the presence of out-of-plane motion poses a significant problem for 2D scan matching. To solve this problem, we propose Level Plane SLAM, an IMU-based global stabilization method for out-of-plane motion compensation. To remove something, you first need to be able to find it. For our method to remove out-of-plane motion from our raw scans, shown here as the black dot, we need to be able to measure the pitch and roll of our platform, which is causing this out-of-plane motion, theta and psi. By incorporating an inertial measurement unit, or IMU for short, we can leverage the information about the platform's orientation that was not previously available to us. By then fusing this orientation with our incorrect LiDAR scans, we're able to generate their correct representation, shown here in red. Now that we've realized the out-of-plane motion component in our scan within the world frame, we can easily remove it. All we have to do is project it down onto the XY plane. The result is the correct 2D representation of our original LiDAR scan, shown in green. Mathematically, this process starts with raw LiDAR scans, shown here having no 3D component, but an out-of-plane motion, so the Z value is always 0. This is then placed within a homogeneous matrix so that it can be transformed from the reference frame of the LiDAR to the reference frame of the IMU using a homogeneous transformation. The rotation and translation are a function of how the LiDAR and IMU have been mounted. At the same time, the IMU measurements are being fused together into the platform's orientation using a Madrick filter. The resulting platform orientation is then converted into a rotation matrix to transform the LiDAR scans from the IMU reference frame into the world reference frame, meaning that the LiDAR scans will now have the orientation of the platform at the time that they were generated. And this is what that looks like. So you see our original scan shown in black has now been transformed into the red scan, having a 3-dimensional component, meaning that the Z is no longer always 0. We then remove this out-of-plane motion component by projecting our scan onto the XY plane of the world frame. All of our out-of-plane motion is perpendicular to our XY plane, so its projection is 0. From a practical standpoint, since our points are defined in Cartesian coordinates, this is done by simply dropping the Z value. The result is the correct 2D representation of our original LiDAR scan, which can now be used for traditional scan matching and SLAM. But these scans have one key advantage over traditional planar LiDAR scans. That advantage is that they reduce the scan matching complexity from 3 degrees of freedom to 2 degrees of freedom for our scan matcher. As I explained earlier, with traditional scan matching, you're required to estimate the rotation and translation of the scans. But with our method, the rotation of the scans in the world frame is accounted for by the IMU measurements and their fusion with the LiDAR scans, meaning that these scans are already aligned rotationally and aligned translationally, reducing the degrees of freedom from 3 degrees to 2 degrees of freedom, as you can see here in both of our animations. Now, how well does our method perform? To begin, we do a small-scale SLAM experiment where we keep the helmet platform shown here on top of a cart level. The cart then navigates the 9.64 meter path through the office detailed in this video. The helmet was kept flat so that different levels of synthetic out-of-plane motion could later be added in the range of -5 to +5 degrees and -10 to +10 degrees. Afterwards, we could then observe the impact of each level on our method and the control method, HectorSlam. HectorSlam is a SLAM algorithm that also uses an IMU and is popular for robots running robot operating system. Here is the results of our experiment. The first row shows HectorSlam, and the second row shows ours. The gray shown here is free space, whereas the black is occupied space. This green color is unexplored, and then this light green represents the path that the robot took. As you can see, when no synthetic out-of-plane motion is added, both maps are identical and a great representation of the original map. Now, when we start to add some synthetic out-of-plane motion, we start to see issues with HectorSlam not being able to create correct matches, whereas ours is still converging to the true map, which is shown here. When we add our final level of synthetic out-of-plane motion, HectorSlam is no longer able to produce a usable map for path planning or navigation, whereas ours, once again, shows no signs of degradation due to out-of-plane motion. We now move on to our second validation. In this large-scale SLAM experiment, I wore the helmet as I navigated through the hallways of the university. The levels of out-of-plane motion experienced by the platform as it traversed the 75-meter path can be seen in this video. The later sections of this video have been sped up since, in total, the experiment took 75 seconds. We have once again compared our method against that of Hector SLAM. And here are our results. As you can plainly see, this level of out-of-plane motion was too much for Hector SLAM to generate a usable map, whereas ours was able to generate a map that was unaffected by out-of-plane motion. Which brings us to our conclusion, that out-of-plane motion poses a significant problem for platforms like drones or wearables. If not properly accounted for, it leads to the generation of maps like this. But by applying level plane SLAM, you're able to account for and remove out-of-plane motion, leading to more robust scan matching and 2D SLAM. Additionally, level plane SLAM is well suited for real-time applications, having an average runtime of 4.76 milliseconds, which is 2 milliseconds faster than the scanning rate of our LiDAR. I would like to acknowledge the City of Oshawa for their contribution, as well as the Queen Elizabeth II Scholarship in Science and Technology. Thank you for listening.